Alright, I thought what we would do today is have a very simple look at the eye. And as a neuroscientist, cognitive neuroscientist, I'm mainly interested in how your eye is used to see, but there's a lot about the eye, different muscles, a lot of different nerves. I want to talk a little bit about all of that. And if you find this interesting, then we can talk more at some point about how the eye actually sees. But I try to give a general overview today. And I also teach sensation and perception. So theoretically, I could do this for all of our senses. Because I think I have models. I think I have models for everything. I just don't have access to them right now necessarily. But let's stick to the eye for now. Okay, so what can we say about the eye? Well, your eye allows you to see. But first, let's talk a little bit about the muscles. There are muscles inside the eye, outside the eye. I mainly want to talk about the muscles on the outside of the eye for now. So what do you have? Well, if I rotate this model a bit, sorry about this interesting tablecloth, but I wanted something to dampen the noise a little bit when I fiddle with the model. Your eye needs to move, of course, because you need to be able to look at different areas of your field of vision, right? Of your world, right? You need to be able to look at things. So you have four muscles called rectus muscles. This is one, and you can see why it's called rectus, right? Straight muscle. This is the lateral rectus muscle. If you look at this eye, in case that was not clear to you, would be entirely understandable. So this would be the bony orbit, right? That's, call it your eye socket. This is the outside of your skull, and this is towards the side of your nose, right? So a lateral rectus muscle is on the lateral side, on the side away from the midline, and then on the other side, I can open that up for just a second, here you have a medial rectus muscle. Now those muscles are relatively straightforward. When this lateral muscle, the lateral rectus muscle contracts, then your eye will move towards that side. So in anatomical terms that is abduction, right? Something moves away from the midline of the body. If the medial rectus muscle contracts, well then you get adduction with two D's, moving towards the midline. So your eye would move to, so your pupil, so to speak, would move towards your nose, right? And otherwise it moves away from that. Then you have a superior rectus muscle, and at the bottom, which is a little hard to see, but at the bottom is an inferior rectus muscle. At the bottom there, right? So your eye can move up and it can move down, right? So that can happen. Then you have a inferior oblique muscle, which is there, which allows you to do extorsion. So in other words, your eyeball can also rotate a bit. This is very easy to see. If you move your head around to a degree, right, your eyeball stays straight so that your horizon stays straight. You can easily see this in a mirror. And after a certain point that doesn't work anymore, then your whole world rotates, right? So your eyes are kept, your eyeballs are kept kind of straight, and that's done by your inferior and superior oblique muscles. So that's the inferior oblique muscle. Then here is a very interesting anatomical structure. The superior oblique muscle, which runs through, so it's a muscle, I was actually pointing at tendon, this is the actual muscle, which sends out a tendon through a little bony structure there, which is basically a pulley, right? And that little structure is called trochlea, which is Latin for pulley. And that can do intorsion, so that can rotate your eye towards the midline, so towards your nose. And the inferior oblique muscle does extorsion, rotates your eye toward the lateral side, towards the side, away from your nose. Now as to the innervation, remember that your brain has cranial nerves, and those cranial nerves allow your brain to communicate with the sensory organs and also to control certain muscles in this case. So almost all those muscles are controlled by the little cranial nerves you see coming out there. Cranial nerve number 3, the oculomotor nerve. And the oculomotor nerve controls the superior and inferior rectus muscles, the medial rectus muscle, the inferior oblique muscle. Yes, sorry, I had to come up with a name there for a second. And that's pretty much it. Now then you have the lateral rectus muscle, which is controlled by the abducens nerve. Remember, that abducts the eye, makes it turn away from the midline. The abducens nerve is right there, right? Right there you have two of each, right? So there's two of those as well. And then finally, you have this strange superior oblique muscle which runs through the pulley, remember, trochlea, and that's controlled by the trochlear nerve. And the trochlear nerve, it's a little hard to see, I'm just going to remove that cerebellum there. You see this thing at the back here? Well, that's the trochlear nerve. That's the only nerve that comes out of the back, okay? The back of the brainstem, which is interesting. The rest, all the other cranial nerves coming from the brainstem come out of the front. Interesting. Or side, I guess, but this is the only one coming from the back. Okay, so that's a lot of stuff about muscles, but what about actually seeing? Well, as I said, I don't have my proper retina model, but we'll get to that one day. An eyeball. There's all kinds of stuff. There is veins and arteries, but there's also nerves. I don't want to get into that too much because that becomes really complicated, and that's a good one for anatomists. Okay, so pull that off there. There goes our superior rectus. Now we have the eyeball. Let's focus on that for a little bit. Not on its movement necessarily, but what's going on the eyeball. What does an eye do? What allows you to see? How does it allow you to see? It focuses light that is reflected off of objects, or that comes directly from a light source, but typically that is reflected off of objects. Right now, light bounces off this model into the camera lens and onto a sensor. Well, that's basically what your eye does as well, right? You have a structure that focuses light and focuses it onto nervous structure, nervous tissue, sorry, that allows you to then see. We'll get to that. So how does light get focused? Well, the first thing that focuses light is this on the outside. And do you know what the name of this is? Now, if you said lens, that would be very understandable, but this is not your lens. That's your cornea. The cornea, and actually the cornea does most of the focusing of light, which is interesting. That's transparent tissue. Now, if I open up this eye, it's always a little bit of fiddling. See what I mean? Okay. I had to adduct. Okay. So we have cornea there. Yeah, cornea. Okay. What else do we have? Well, then you have this eyeball, which is now moved a bit. Okay. So we have some darker tissue. Let's not get into the layers of tissue, because that, again, that's a fun one for anatomists, but I'm more interested in the cognitive neuroscience of this. So let's say that I just take this out so that I can show you. Okay. Now I have an eyeball. Let's take this out. That gets that out of the way. Okay. Now I have an eyeball, and I think I can zoom in a bit in this eyeball. Okay. So what do you see? Well, there's a couple of things. There's your iris. Your iris is what gives your eye color. In this case, happens to be blue. Okay. Now, the complicated structure, but that iris, if you've ever seen one of those good old-fashioned diaphragms on a camera, right, that can sort of close and open up. You know what? Give me 1 second. Okay. Sorry for the interruption. We now continue with our regular program. Here's my little steamer basket. Okay, this is exactly what your iris does in a nutshell, right? So you see, if this would be your pupil, the opening in the iris, look at what happens. It can get bigger or it can get smaller, right? A type of sphincter muscle, really. So we have that. That's what gives your eye the color, right? Blue or brown or green, etc. So we have that. Now, in that iris is an opening, and that opening is the pupil, right? And the pupil can constrict or dilate depending on light circumstances, but also depending on what's going on in your life. What I mean by that is this. So, of course, if you are in a very dark room, your iris will dilate. Sorry, the pupil will dilate, right? So that more light can fall in. But if you are in a very bright environment, then your pupil will constrict, right? So that less light falls into the eye. You all know what this is like. If you've been in a dark building, you step outside on a bright summer's day or something, and you kind of get this sort of pang of pain in the back of your eye. Well, guess what? Too much light hitting your retina, it doesn't work so well. I'll get to the retina. So that's a very important aspect, a very important function of the pupil, right? The pupil just gets bigger or smaller because of your iris kind of constricting or dilating. Okay, what else do we have? Well, right in front of this, so remember you have this part of your eye, right? So in between the inside of the cornea and your iris, you have the anterior chamber. And the anterior chamber of your eye is filled with aqueous humor. Not humor as in haha, but humor as in a liquid. And that liquid gets refreshed continuously. Okay, that's the anterior chamber. Then what else do we have? Well, your eye is lined on the inside, I'm now pointing at the outside, right? It's lined on the inside with neural tissue called the retina, and the retina actually collects light. So that has photoreceptors, and you know about photoreceptors because you've heard about rods and cones. Those are your photoreceptors that actually register light. They pass on a signal to the bipolar cells, and they pass on a signal to the ganglion cells, but I don't have my retina model, so that will have to leave for another time. I don't want to make this too long anyway, and it probably is going to be long anyway. So, okay, if I open up this, then what do we see? We had the anterior chamber, right? Aqueous humor. Then you have this vitreous humor. This is not actually a thing you can take out of the eyeball. This is basically a cast of that liquid. I'll get back to that liquid, okay? Vitreous humor. What do you have here? Well, that is your lens, okay? This is your lens. And that's kind of what it looks like. Now, your lens can change shape. So you have specific muscles, okay, kind of pushing and pulling on that lens so that it either stretches out and gets thinner. That allows you to look at things in focus that are far away. Or it kind of compresses your lens, makes it thicker. And that allows you to see things up close. For example, when you read something, that's what happens, right? It's the process of accommodation. And that happens because there are sort of ligaments suspending that lens, and there's a ring of muscle around it that can push and pull. Okay, now earlier I talked, that's the final thing I'll say about the iris, because I said it's not just a matter of light coming in, it's also a matter of what's going on in your life. So another thing that I forgot to say then, that's why I'm adding it in now, is that your pupil can also dilate or constrict depending on what state you are in. If you are in a state of arousal, and remember for a cognitive psychologist, cognitive neuroscientist, that can mean all sorts of things, but something is happening that's drawn your attention, your pupils can dilate, right? This is a fight or flight thing. So if you're in danger, remember, like I don't know, deer in the headlights or something, right? Eyes open widely and your pupil dilates, so a lot of light falls in. Whereas if you're completely relaxed, then your pupil can just constrict. You don't need so much light coming in. Okay, so we have that kind of fits together with your lens, more or less sort of accommodating, right? Let's put that topic together. So that's what can happen to your lens. Okay, that lens focuses light so that it hits the back of the retina, right? The back eyeball is lined with these photoreceptors like rods and cones. Now, this whole thing, right, this vitreous chamber is filled with vitreous liquid, which that vitreous humor is, this is basically a cast of that. So again, this is not a thing that you could pull out of someone's eye. It's this kind of liquid. This liquid is much thicker. And whereas the liquid in the anterior chamber gets replenished and refreshed all the time, this liquid pretty much stays the same throughout your life. It doesn't get refreshed. Why does it matter? Well, if you've ever experienced a floater, and as you get older you experience more and more of those, right? You know that, like you step outside, it's bright out and you see these little sort of things floating in your eye, right? They're in this liquid, and because this liquid doesn't get refreshed, once you have them, and they won't leave. And for the record, you don't actually see them because you can't focus on them, because they are behind your cornea, which does most of your focusing, and then you have a lens which does the rest of the focusing, and those floaters are in here, they're behind the cornea and behind the lens. So what you really see is their shadow. Light passes through all those focusing structures, and those light beams are kind of, you know, they hit one of those floaters, and that casts a shadow. And the shadow on your retina, that's what you really see. Now the final thing is, I think, two more things I wanted to point out. You have a little spot, a little bit to the kind of, yeah, it's about there. You can see that in that vitreous humor cast, but you can also see it here in the back of the eyeball. See that? So there is one spot on the back, a little bit about there, I would say, right? That is very, very rich in cone photoreceptors, and the cones allow you to see things in focus. They need a lot of light, but they allow you to see things in focus and in color. And those photoreceptors are concentrated very heavily in a small depression, I'll show you that another time, on your retina called the fovea, which is Latin for pit. And that is part of your macula. You may have heard of that term, which also contains some other areas. So that's an area that's very rich and dense in cones. Now, so that's really what allows you to see in focus, and that area is very small. If you stick out your hand like this and you look at your thumbnail is the only area that's actually foveatic. So that's the only part of your field of vision that's actually in focus. Because everything, all the other light that hits outside of your fovea actually doesn't lead to an image that's in focus. That's how amazing your brain is. It just sort of interpolates and has some other processes to make sure that you actually see. It seems like all of your world's in focus, but only that tiny bit of your thumbnail is in focus. And that's because that fovea is so small. I mean, look at this little purple dot and how much space that takes up in this entire back of the eyeball. Okay, so again, we'll do the big vision part another day, but in a nutshell, you have photoreceptors which provide output to a next layer called bipolar cells, and they provide output to another layer called the ganglion cells. I'll show you this one day. All those ganglion cells have little processes, axons, right, which are used to conduct a signal, and all of those axons are kind of bundled up, and they form this thing, this yellow thing. Okay, so if I put this back together, I'm going to leave out the lens and all that. Okay, this is not easy to put together if you're not looking at it straight on. This provides output from what you are looking at into your brain. This goes into your brain. Now, if I reconstruct this model, I'm just going to take off these bits. Put this thing back in. Okay, so now there's all kinds of parts missing, but you'll get the basic point. Maybe I should try to put this back in. I don't know why this is so hard. Okay, there. How does your brain get that information? Well, look at what happens in the back here. Is this secure? It seems to be secure. Okay, can I also do it this way? Oh yeah, I can just let it rest. Fantastic. Okay. Eye, front, pupil, light comes in, focused by the cornea, focused by the pupil, hits the retina, in particular the fovea, because you're looking at something that is foveatic, that's in focus. Then you have those photoreceptors, the cones, right, in your fovea, providing output to the bipolar cells. To the ganglion cells as axons all bundle up, they leave the back of the eyeball, and then you get to this bit. And this bit is the second cranial nerve, that's the optic nerve. If you were to snip this in half, someone would be blind in that eye. If this gets compressed by something, say a tumor, someone would get vision problems. This is the output of what you see to your brain, or let me say what you sense to your brain. Your brain then has to interpret that signal. That's a whole different can of worms. We'll get to that one day, but not today. So what you notice here, that's the final thing I wanted to say. If I move up this superior rectus muscle a little bit, of course it doesn't stay up by itself. Note what happens. So you have here your right eye, optic nerve, and now notice this little split going on here. Yeah, very interesting. Remember, this is the side of your temple, and this is the side of your nose, right? Your retina basically is split in half. There's the temporal hemi-retina, the half of your retina on the side of your temple, and the nasal hemi-retina, the half of your retina on the side of your nose. Okay. The optic nerve collects all the information, and there's a split. The part of your visual field that stimulates the nasal, now let me first do the temporal part of your retina, right? So that side of your retina, this side, right? Travels down, stays on the same side of your brain. But this end, the part of your visual field that stimulates the nasal half of your retina, in other words, the half of your retina on the side of your nose, travels down and travels to the other side of the brain, becomes contralateral. It's very complicated. And in your other eye, the exact same thing happens. So the part that's close to your nose will cross over to the other side of your brain, and the part of your retina that gets stimulated on the side of your temple, that half of the retina, will stay on the same side of the brain. So in this case, right eye, temporal hemiretina will go to the right half of the brain, and for the left eye it would stay on the left half of the brain. And that is the optic chiasm, where your optic nerves, here you have them again. So that's your optic nerve, right? You have two of them, of course, one for each eye. They cross over, and they cross over the optic chiasm. And that has specific, there are specific uses to that, and we'll get to that probably one day. Okay, that's a lot of information about the eye, so I should absolutely leave it at that. I hope this was interesting and a little useful, has given you some insight into anatomy. And that's it. Let me know if this was useful / interesting, and we can do this for another sentence or something. Bye!